Good morning, students. Today we'll start section 3 of complex analysis, and our first topic is maximum modulus principle. So according to this principle, if we are given an analytic function f of z which is analytic within and on a simple closed contour C, and this function is not constant, then we are to prove that mod of f of z attains its maximum value on the boundary of contour C and not inside. It means if m is the maximum value of mod of f of z on and within C, then for every point z within C, f of z mod will be less than m. It means the maximum value of mod of f of z that is attained on the boundary, not inside the contour C. And in order to prove this principle, we use contradiction method. Let us take m is the maximum value of mod of f of z, and this is not attained on the boundary of contour C. Let us take this maximum value that is attained inside the contour C at the point z is equal to a. Therefore, we can write f of a mod is equal to m, where m is the maximum value of mod of f of z. Now, because m is the maximum value, therefore we can say that f of z mod will be less than or equal to m for every point z inside the contour C. Now this is the contour C. Let us take a circle gamma having the center at the point P dash. The center of circle gamma is A, and this circle gamma that is lying inside this contour C. Now because we are given function f is analytic function, so that is continuous, and therefore by continuity of this function there will exist a point z is equal to b inside this circle such that mod of f of b is less than m. Because mod of f of b that is less than m, so let us denote mod of f of b be given by m minus epsilon, where epsilon is greater than 0. Now because f of z that is continuous function, so its modulus will also be continuous inside the contour C. So we can say that mod of f of z that is continuous at the point z is equal to b also. Now we can use the definition of continuity at the point b. So by definition of continuity, for epsilon greater than 0, there will exist positive number delta such that whenever mod of z minus b is less than delta, the absolute value of mod of f of z minus mod of f of b that is less than epsilon by 2. Now we know that mod of f of z minus mod of f of b that is less than this quantity, and this quantity is less than epsilon by 2. So from here we have obtained mod of f of z minus mod of f of b that is less than epsilon by 2. So from here we can say that mod of f of z will be less than mod of f of b plus epsilon by 2. Now mod of f of b that is m minus epsilon. So this will imply mod of f of z will be less than m minus epsilon by 2. So we have obtained mod of f of z is less than m minus epsilon by 2 for every z whenever z minus b mod is less than delta. Now let us draw a circle of radius delta and center at the point z is equal to b. The equation of this circle is given by z minus b mod is equal to delta. Now we can use the equation 4 because whenever z minus b mod is less than delta, f of z mod is less than m minus epsilon by 2. Now let us draw another circle which we have denoted by the circle gamma dash having the center at the point P dash. Center is A and the radius we have taken as a minus b mod. So equation of this circle can be written as z minus a mod is equal to r. Here r is mod of a minus b. Now let us take this circle intersects this circle at the points P and Q, and the angle P dash Q that we have taken as alpha. Now because the function f is analytic function, and therefore we can use Gaussian integral formula to find the value of the function at z is equal to a. So f of a is given by 1 upon 2 pi iota integral f of z divided by z minus a dz. This integral is over the circle gamma dash. Now the equation of the circle gamma dash is given by z minus a mod is equal to r. It means z minus a is given by r e raised to the power iota theta. Differentiating from here, dz is equal to r. The derivative of e raised to the power iota theta will be e raised to the power iota theta into iota d theta. Now substituting the value of dz and z minus a here, this will become f of a is equal to 1 upon 2 pi iota integral the limits of theta are 0 to 2 pi for the circle gamma dash fz as it is. The value of dz is r e raised to the power iota theta into iota d theta. The value of z minus a is r e raised to the power iota theta. Now these two terms are cancelled out, iota is cancelled with iota, so we get f of a is equal to 1 upon 2 pi integral 0 to 2 pi f of z d theta. Now let us break this integral into two parts. One integral we have taken between the limits 0 to alpha, and second we have taken from alpha to 2 pi. Now let us multiply this equation throughout by 2 pi and taking modulus on both sides. So we get 2 pi into f of a mod will be less than or equal to integral 0 to alpha f of z mod d theta plus integral alpha to 2 pi f of z mod d theta. Now for the circle gamma, f of z mod is less than m minus epsilon by 2. This is from the equation number 6. And from the equation number 2, for the circle gamma dash, f of z mod is less than m. So we have substituted the values. Now simplifying these integrals, we get 2 pi into f of a mod is less than m into 2 pi minus epsilon alpha by 2. Now dividing through by 2 pi, we get f of a mod will be less than m minus epsilon alpha divided by 4 pi. Now f of a mod, that is m, so we get m is less than m minus epsilon alpha by 4 pi. But this is a contradiction, so this proves that our assumption is wrong. It means f of z mod attains its maximum value on the boundary and not inside C. And this completes the proof of maximum modulus principle. Now our next principle is minimum modulus principle. According to this principle, if a function f is analytic within and on a simple closed contour C, and this function is non-zero inside C, and this function is not a constant function, then we are to prove that mod of f of z attains its minimum value on the boundary. It means if m is the minimum value of mod of f of z inside and on the contour C, then for every point z inside C, f of z mod will be greater than m. It means minimum value of mod of f of z will be attained at a point on the boundary of contour C. In order to prove this principle, you will have to prove maximum modulus principle. Now because here the function f of z is analytic within and on C, and the function is non-zero inside C, so its reciprocal that will also be analytic function within C, and we can use maximum modulus principle. So by maximum modulus principle, mod of this function attains its maximum value on the boundary of C, and therefore its reciprocal will attain its minimum value on the boundary of contour C, and this proves minimum modulus principle. Now next there is an important lemma which is called Schwarz lemma. Now we discuss this lemma. According to this lemma, if we are given an analytic function in a domain z mod less than 1 and f of z mod is also less than 1, value of function f at z is equal to 0, that is 0. If these three conditions are satisfied, then mod of f of z is less than or equal to z mod, and also mod of f dash 0, that is less than 1. And the equality holds here in this part if f of z is linear transformation given by w is equal to z e raised to the power iota alpha. Here alpha is some real constant. Now to prove this lemma, let us take a circle C having the equation z mod is equal to r. Center is 0, radius is less than 1, which we have denoted by r. Now because we are given function f is analytic function, so we can write its expansion by using Taylor's theorem. So for any point z inside the circle C, f of z is given by a0 plus a1z plus a2z square and so on. Now let us put z is equal to 0 here. Left side will become f of 0, and on the right side all the other terms will become 0, only a0 is left. Now f of 0 is 0, we are given in the statement, so we get the value of a0 which will be 0. Now substituting the value of a0 in the equation 1, we get f of z is equal to a1z plus a2z square and so on. Let us divide throughout by z. So this will become f of z divided by z is equal to a1 plus a2z plus a3z square and so on. Now let us denote this function by capital Fz. Now we can see from here that for z is equal to 0, this function will not be defined. It means this function has a singularity at z is equal to 0. Now let us remove this singularity by taking the value of this function f at z is equal to 0 defined by a1. So in this way we have removed the singularity at z is equal to 0. Now let us take z is equal to a is any point on the boundary of this circle, and therefore we can write a is equal to r e raised to the power iota theta. Now we can use maximum modulus principle. According to maximum modulus principle, because this function is analytic function, so its modulus will attain the maximum value at the boundary of circle C. So we can say mod of f of z attains maximum value at z is equal to a. This is the point on the boundary of the circle C, and because f of a mod, this is the maximum of mod of f of z, so f of z mod will be less than its maximum value. Substituting the value of capital Fz, this is small f divided by z, so f of z mod is less than maximum of mod of fz upon z. Now because we are given in the statement f of z mod is less than 1, so this will be less than 1 by z mod, and because z mod is equal to r, so we have obtained f of z mod will be less than 1 by r, and this approaches to 1 as r approaches to 1. So we have proved f of z mod is less than 1. Substituting the value of this f, this is small f divided by z. So from here we get f of z mod will be less than z mod. Now to prove the second part of the lemma, let us take z is equal to 0 in this equation. From here f of 0 mod is less than 1, but we are having f of 0, that is a1, so a1 mod will be less than 1. Now the function small f is having the expansion a1z plus a2z square and so on. Let us differentiate both sides with respect to z. This will become f dash z. Here we get a1 plus 2a2z plus 3a3z square and so on. Putting z is equal to 0 here, this will become f dash 0 is equal to a1. Now because a1 is less than 1, so we have obtained mod of f dash 0 is less than 1. So this proves the second part of the lemma. Now because z is arbitrary point, therefore for every point z having z mod less than or equal to 1, f of z mod will be less than or equal to z mod. Now in this part, the equality holds at a single point, then it means f of z mod attains its maximum value, and therefore by maximum modulus principle that will reduce to constant, and therefore we can say that f of a mod is equal to 1 holds only when f of z by z is equal to e raised to the power iota alpha. It means f of z is equal to z e raised to the power iota alpha. Here alpha is some constant. So this completes the proof of Schwarz lemma.